This is the solution video for question 3 of the modules of Moore's circle of 3D stress and static failure theories. In this question, we've been given a short concrete cylinder which has the diameter of 50 millimeters and is subject to a torque of 500 newton meters and an actual compressive force of 2 kilonewton. We need to determine if it fails according to the maximum normal stress theory. We've also been given the ultimate stress of the concrete as 28 megapascals. So we're going to start by noting out what we have been given. We have a diameter of 50 millimeters, same as 0.05 meters. We've also been given a torque of 500 newton meters, a normal force of negative 2 kilonewtons, it's compressive, and we've been given the ultimate stress for the concrete as 28 megapascals. So a way to approach this question is by doing this in steps. So step 1, free body diagram, and drawing out our elements. In this case, the free body diagram it's fairly simple. It's basically just a copy of what we have above. So our cylinder, we have our compressive force, 2 kilonewtons. We also have been given the torque, which is given us 500 newton meters in both sides of the element, of the cylinder. And when we think about our element, we think about it kind of like we take a measurement, say in this little square here. So we're going to draw out the element. And the way we want to think about it, well, first of all, let's give this an axis. So the cross here is my y-axis, then my element will have y on x. As such, my 2 kilonewton force will then cause a stress in the normal axis y. So stress in y caused by our normal force divided by the cross-section area. So our cross-section area is then referring to, if we look at our free body diagram, it's just looking at the cross-section area in this element. So it's just a circle. But then we also have a shear stress caused by the rotation. Just going to assume that it's positive as such. And then my shear stress, xy, is just my torque times the radius of the cylinder divided by my rotational moment of inertia. And the rotational moment of inertia depends on what the cross-section looks like. So for a circle, for example, our J is just pi on 2 times our diameter on 2 to the power of 4. This is for a circle only. So then for our step 2, we're going to go ahead and calculate our stresses. And for our normal stress in Y, this is pretty simple. We've been given our force and we just need to figure out the area. So I'm going to do negative 2,000 newtons divided by my area of the circle. And just recall quickly, 1 megapascals is the same as 1 Newton per millimeter squared, right? So when I do the area for this one, I can keep it in millimeters just to get my value straight away. So pi times the radius, so 50 on 2 squared, and I will get negative 1.019 megapascals. And just be careful when you do your shear stress, because then we want to transform our values to meters because we do use the rotational moment of inertia. So we will have our torque times our radius on J. So I'm just going to put the equation in there for J, pi on 2, diameter on 2 to the power of 4. Again, just for a circle. So what I have is 500 times in meters this time, 0.05 divided by 2 to get the radius, pi on 2, 0.05 on 2 to the power of 4. And what we'll get is a shear stress of 20.37 megapascals. For our step 3, we want to find our principal stresses. And rather than going all the methods through Mohr circle and whatnot, we're just going to do this quickly from what we already know. So our principal stress 1 and 2 is the same as our center of Mohr circle plus minus the radius, and that way we can find the maximum and minimum. So if we write this out in terms of their equations, so principal stress 1 and 2, center point, again, it's just our average, so it will be our stress in X plus the stress in Y divided by 2, and radius, because we have a square root, plus minus square root of our normal stress in X minus normal stress in Y divided by 2 squared plus our shear stress squared. In here, we don't have an X, we simply just have our normal stress in Y. So 0 plus minus 1.019 divided by 2 plus minus square root 0 minus 1.019 2 squared plus our 20.37 shear stress is squared as well. If we then put this in our calculators and calculate our maximum, so maximum being the center plus the radius, we get 19.87 megapascals. And for our minimum principal stress, we get negative 20.89 megapascals. So we're not done there. We have our final step. So step 4. we want to find if this is safe. So we're going to apply the maximum normal stress theory. And what does our maximum normal stress theory say? Well, it says that the absolute value of our principal stress 1 should be smaller than our ultimate stress. It also says that our absolute value of our principal stress 2 should also be smaller than our ultimate stress for the material. And if we then input the values that we had, so for our maximum, we had 19.87, which in fact is smaller than 28 megapascals. So in terms of that, safe. Principal stress 2, take the absolute value of 20 minus 20.89, so we just get 20.89. And again, it's smaller than our ultimate stress for the material, which means that it's safe. And that summarizes this question.